Hi everyone, welcome to Go Classes. So let's start the session now. Okay, so let's start now. So we were discussing graph theory. So in the graph theory marathon, what we are doing the revision of graph theory. Complete graph theory we will revise and we will solve almost all the gate previous year questions of graph theory because graph theory is very important subject topic from the gate exam point of view. As I told you, every year at least two questions are coming from graph theory. Okay, last year from graph theory 6 marks of questions came. Okay, last year. So you can notice every year I can say you can you can get 4 to 6 marks from graph theory. So this graph theory is very important, and that is the reason we are having this graph theory marathon. Okay, also for the remaining topics of discrete mathematics, in discrete mathematics you have other topics like mathematical logic, first order logic, propositional logic, combinatorics, set theory, function relation. Okay, so all these topics are already covered. Okay, the revision plus gate questions, okay, the revision of all these topics is already over, is already complete. On the Go Classes YouTube channel you can find. Okay, so now let's start. So before we start, please tell me, audio video volume, is everything clear? Let me know audio video volume, is everything fine? Okay, so let's start. This is our graph theory marathon part 2. Okay, graph theory gate PYQs and revision part 2. Okay, so we will do the revision and also we will solve the gate PYQs. Let's start. Okay, so let me introduce myself. Okay, anyway, let's ignore this. Okay, so let's save some time. Okay, so let's move on. Okay, so just I want to tell you this point that if you want to attempt Go Classes and GATEOverflow mock test, okay, so all the 15 mock test, total 15 mock test you can attempt. All these, all the 15 mock test of GATEOverflow plus Go Classes, if you want to attempt, okay, the best quality mock test you want to attempt before the gate exam, then you can purchase this package. This mock test package you can purchase, the link is in the description. Okay, so if you have already purchased, if you have already enrolled for the complete test series for GATEOverflow plus Go Classes combined test series, if you already have, then you don't have to subscribe for these mock test. Okay, but if you don't have this complete test series, then you can subscribe for all the mock test, all 15 mock test you can attempt before the gate exam. Okay, so let's start now. Let's see. So these questions we have done, right? In the last two sessions, these 12 questions are over. Okay, degree of graph. As you can see, this is important topic. A lot of questions are coming from this. Okay, so all these 12 questions we have already done. In this session, we will do these questions. This is our target for this session. Okay, so this session we will solve these questions and some variations, some TIFR questions also we will solve. Okay, some TIFR questions also. So let's see, let's start. So let's start with our question type 2. This type of questions also come in the gate exam, counting graph. Okay, so let's start with our first question. So tell me, what is the answer for this question? This is GATE Computer Science 2001 question. So the question is saying that how many undirected graphs, not necessarily connected, how many undirected graphs can be constructed from this vertex set? So all the vertices are labeled, you can notice, correct? All the vertices, these are labeled vertices. Okay, v1, v2, vn, these are the labeled vertices. Total n vertices you have. How many undirected graphs we can create? Okay, so let's solve this. So you can notice we have total n vertices. So number of vertices is fixed, right? Okay, so these vertices, for example, let's consider 4 vertices. Let's consider if you have 4 vertices, these are your 4 vertices, a1, a2, a3, a4. These are the 4 vertices. Then how many graphs I can create? So number of vertices is fixed. Okay, so that number of vertices you cannot change. So what can you change? Tell me. If number of vertices is fixed, then what can you change? What can you decide? Like how can you create the graph? By putting the edges, right? Yes or no? All you have to do is decide which edges we are putting. Okay, so basically the edges we just have to decide which edges we want to put. Okay, decide on edges. So very simple, that we have to decide how many edges we want to put and which edges we want to put. So for example, if I take this graph is different from this graph, because remember, these are labeled graph. Okay, these are labeled vertices. So you can notice all these 4 vertices are labeled. Okay, so because all these 4 vertices are labeled, these are labeled vertices. So remember, because of labeled vertices, these graph are different. For example, a b c d, this graph is different from this graph. Okay, a b c d, these two graph are different, because here you have here a comma b are adjacent, here a comma c are adjacent. So these are different because of labeled. Okay, the reason is very simple, because of labeled vertices. Okay, because we have labeled vertices, so that is the reason these two graph are basically different. Yes, they are isomorphic graph. These two graph, if you notice, for example, let's call this graph g1, let's call this graph g2. Yes, they are isomorphic. Okay, this is the symbol for isomorphic. Yes, these two graph are isomorphic, but these two graph are different. Okay. So now we have to decide on edges, how many edges we want to put and where we want to put. So you tell me a simple question I am asking, how many positions are there for edges? Like maximum how many edges I can put? Can you tell me how many edges maximum I can put? So you can notice between every pair of vertices you can put edge. Yes, between every pair of vertices you can put edge. So you can notice that maximum how many edges I can put? Maximum number of edges. Okay, maximum number of edges possible. What is the maximum number of edges possible? That is basically from these 4 vertices, you are selecting 2 vertices, right? Yes or no? So select any 2 vertices and you can put edge, correct? Whatever 2 vertices you put, whatever 2 vertices you select, you can put, you can make them adjacent, right? Yes or no? So what is the maximum number of edges we can put? Select any 2 vertices. Okay, select any 2 vertices and you can put one edge between them. For example, you can select these 2 vertices and you can put, so select any 2 vertices and put edges. So in this graph total 6 edges we can put, right? Yes or no? In this graph total 6 edges we can put. So I can say that maximum number of edges that you can put is nc2. Okay, just select any pair of vertices and you put and you make them adjacent. Okay, so this is the maximum number of edges we can put. Now you can notice that for every edge we have 2 possibility. Do you agree? When I am creating a graph, this graph I am creating, then for every edge I have 2 possibility. Do you agree that for every edge there are 2 possibility? Either you put it in the graph or you don't put it in the graph. So I can say that for every edge, okay, there are 2 possibility. There are 2 possibility. Either you put it in the graph or you don't put it in the graph. There are 2 choices. Do you agree that there are 2 choices? Yes or no? Okay. So for example, this edge. For this edge, there are 2 choices. Either you put it or you don't put it. For this edge, for this pair, look at this pair of vertices. For this pair of vertices, there are 2 choices. Either you make them adjacent or you don't make them adjacent. So for every pair of vertices, there are 2 choices. I can say that for every pair of vertices, for every pair of nodes, there are 2 choices. Either you make them adjacent or you don't make them adjacent. So there are 2 choices for every pair of vertices. What are these 2 choices? These 2 choices are either you make them adjacent, means either you put edge, or you don't make them adjacent, or you don't make them adjacent, means you don't put edge. So either you put edge or you don't put edge. So that is the reason there are 2 choices for every pair of vertices. For every edge, for every pair of vertices there are two choices. So the answer will be these many graph you can create, right? Yes or no? Okay, so how many graph we can create? So these many graphs we can create, because for every pair of vertices, whatever pair of vertices you take, any pair of vertices you take, there are two choices. Either you make them adjacent or you don't make them adjacent. Okay, for every pair of vertices, either you put a's or you don't put a's between them. So for every possible a's, for every pair of vertices, there are two choices. So that is the reason answer will be how many graph we can create is 2 power nc2. Okay, why 2 power nc2? Because how many pair of vertices are there? These many pair of vertices are there. These many pair of vertices we have, and every pair of vertex has two choices. So that is the reason your answer will be how many graph you can create, that will be 2 power nc2. 2 power nc2. And remember what is nc2? Nc2 is basically nn minus 1 by 2. Okay, so the answer is going to be option D. Okay, very simple. Now let's see the next question. Now tell me about this one. What is the answer for this question? This is your GATE 1994, also ISRO 2008 question. So the question is asking the number of distinct simple graphs up to 3 nodes. Okay, up to 3 nodes. How many distinct simple graph we can create up to 3 nodes? Tell me in this question, labeled or unlabeled, is that information given? In this question, vertices are labeled or vertices are not labeled, is that information given to us? Tell me. That information is not given, right? Yes or no? These vertices, they are labeled or not, that information is not given. So okay, so let's assume these are labeled vertices. Okay, so let's assume that if labeled vertices, if vertices are labeled, if labeled vertices, then what will be the answer? If vertices are labeled, then what will be the answer? Okay, so up to 3 nodes, the question is saying up to 3 nodes. Okay, so if vertices are labeled, number of vertices is 1. Okay, number of vertices is 2, number of vertices is 3. If labeled vertices, then the formula we already know. For the labeled vertices, the formula we already know, right? Yes or no? So if you have labeled vertices, then if you have n vertices, then how many graph we can create? For n vertices, number of graph, number of simple graph, what that will be? How many simple graphs we can create? That will be 2 power nc2. Okay, that we have already seen. This we have already seen, that answer will be 2 power nc2. Okay, so you can easily see that using this formula you can solve it. So 2 power nc2. So with one vertex only one graph you can create. That is very like, that is simple corner case. Okay, if you have one vertex, then because of one vertex only one graph you can create. So number of simple graph, how many simple graphs you can create? So number of simple graphs that you can create is only one. If you have two vertices, there are two vertices a comma b, there are two graph you can create, right? Either you can create this graph or you can create this graph. So number of simple graphs that you can create, what is that? Number of simple graphs that you can create will be 2. Okay, now you tell me, if you have n equal to 3, then answer will be 3c2. Okay, 2 power 3c2. So that is going to be 2 power 3, that is going to be 8. So up to 3 nodes, how many graphs you can create? If labeled vertices, then answer will be what? Then answer will be 1 plus 2 plus 8, and that will be 11. Is this given in the options? Is this given in the options? 11. Okay, if you consider labeled vertices, if I consider labeled vertices, this option is not given. It means what? Tell me, it means what? So it means what? Tell me. So the answer will be 11, but that is not given. It means unlabeled, right? Yes or no? So it simply means that the question is talking about unlabeled vertices. So if unlabeled vertices, you can easily calculate. If you have unlabeled vertices, so then you can easily calculate. If n equal to 1, how many graph you can create? If n equal to 2, how many graph you can create? If n equal to 3, how many graph you can create? See, unlabeled vertices, so only one graph you can create here. Okay, so the number of simple graphs that you can create, number of simple graphs that you can create will be 1. Okay, if you have two vertices, then you can create two graph. Okay, so here you can create two graph. These two graph you can create. Okay, if you have three vertices, then either you can create this graph without any edge, or you can create this graph with one edge. Okay, or you can create this graph with two edges, or you can create this graph, or you can create this graph with the three edges. Okay, so these are the possibilities: this graph, this graph, this graph. So if n equal to 3, then number of graphs will be what? Then how many graphs we can create? The number of graphs that you can create will be 4. So if unlabeled vertices, then answer will be 1 plus 2 plus 4, and that will be 7. Okay, so that will be 7, and yeah, the option is given to you, so the answer is going to be 7. Okay, is this clear? So the answer will be 7. For this question, answer will be 7. Now, is there anyone here who is thinking that what about 0 vertices? What about n equal to 0? Okay, is there anyone who is thinking what about n equal to 0, like 0 vertices, graph with 0 vertices, like the graph with 0 vertices, graph with no vertex? What about this type of graph? Should we consider that? Should we consider that? Tell me. Tell me. Should we consider that? See, that is considered. This is your graph. Twinkle. See, twinkle. There is no edge. This graph, this graph, this graph. Total 4 graph. There is no edge. 1 edge, 2 edge, 3 edge. These are the graphs that you can create. Okay. So now I am asking. This is the question I am asking. What about n equal to 0? Graph with no vertex. Should we consider that? Should we consider that? So the answer will be, it depends on the author. It is author dependent. Okay, so graph with no vertices, let me tell you, some authors allow, but most authors do not allow. Some allow, some authors allow, some authors allow. Okay, but remember, I have seen all the NPTEL videos. I can say that NPTEL professors, they do not allow. NPTEL professors, including IISc Professor Sunil Chandran, they also do not allow. So NPTEL professors do not allow. Okay, do not allow. So anyway, there are some authors which allow, but most of the authors, they do not allow. So we will also not allow. Okay, we will also not allow. The answer will be 7. Okay, actually there is no ambiguity. Can you notice there is no ambiguity? Can you observe there is no ambiguity? Even if you consider this, for example, even if you consider this type of graph, then answer will be 8, and that is not in the option. So did you notice this graph, this question has no ambiguity? See, in this question there are some ambiguities whether to consider labeled or unlabeled. If you consider labeled, then answer will be 11, that is not in the option. Now you are thinking that okay, let me consider unlabeled. If you consider unlabeled, then answer will be 7, that is in the options. In the options you have this 7, so the answer will be 7. But there is no ambiguity. If you are thinking that, sir, what about graph with no vertices? Because there are some authors who allow it. Okay, so sir, answer should be 8. You will tell me that answer should be 8, 7 plus 1. If I consider n equal to 0, if I consider graph with 0 vertex, then answer will be 8. But 8 is not in the options. So did you notice that this question has, I can say, no ambiguity in the answer? Okay, the answer will be option C, and there is no ambiguity about option C. Okay, so very simple. Now let's move on. To the next question. Now let's see this. A simple question I want to ask you actually. This is a Go Classes test series question. That is the reason I am asking you. How many unlabeled graph with 5 vertices, with 4 vertices? Number of unlabeled graphs with 4 vertices. This is a Go Classes test series question also. So can you tell me? Right. So number of unlabeled graphs, unlabeled simple graphs. Okay. So how many unlabeled graphs with 4 vertices? Can you tell me? If you want to solve this question, if you want to solve this question, okay, so let's see. If you want to solve this question, always go step by step. Okay, always go step by step. If number of edges is 0, tell me, if number of edges is 0, then what is the number of graphs? Tell me. If number of edges is 0, this is your case 1. Number of edges is 0. 4 vertices you have. With 4 vertices, you have 4 vertices. So number of graph will be what? If number of edges 0, then number of graph will be 1, right? Yes or no? If number of edges is equal to 1, now how many? Again the answer will be 1. Okay, here also number of graphs will be 1. So because if you have one edge, what about if you have two edges? If you have two edges, then what about that? If you have two edges, see, if you have two edges, then either you can have them like this or you can have them like this. See, are you getting my point? If you have two edges, then either you can have them like this or you can have them in parallel. So either they can be either these two edges can be adjacent, either those two edges can be adjacent or they are not adjacent, right? Yes or no? So either they are adjacent or they are not adjacent. So here number of graphs will be 2. In this case number of graphs will be 2. What about if number of edges is 3? If number of edges is 3, okay, you have 4 vertices. If number of edges is 3, either you can have a cycle. If you have a cycle, this graph you will get. Okay, either you can have a cycle or if you don't have a cycle, then what you can get? Then you can get this type of graph. If you don't have cycle, then what you can do? You can get this type of graph. See, either you have cycle or you can get this type of graph where you have degree 3, where you have a degree 3 vertex. Okay, so in this you have degree 3 vertex. In this there is no degree 3 vertex, there is a cycle. And the last possibility, see, either you can have a 3-degree vertex. Okay, either you can have this 3-degree vertex. If you don't have 3-degree vertex, if you have no 3-degree vertex, like in this graph you have 3-degree vertex. So if you don't have 3-degree vertex, there is no 3-degree vertex, then in that situation, only 2-degree, like here you have only 2-degree vertices. So this cycle you can create. Or what you can do, for example, this type of graph you can create. Okay, so you can create this type of graph. Okay, so there are 3 possibilities, right? Yes or no? Is there any other possibility? Can you tell me? Like here you have 3-degree vertex. This is the only graph possible in which you have 3-degree vertex. This is the only graph possible. If you do not have 3-degree vertex, then in this situation, okay, either you have no cycle or you have cycle. Okay, so if you have cycle, then you will get this. Okay, and if you have no cycle, then you will get this. There is no other possibility. Okay, so in this situation you will get this. What about four edges? What about 4 edges? In this graph, if number of edges is equal to 4, if you have 4 edges in this graph, if you have total 4 edges, so with 4 edges what you can do? See, with 4 edges, if you have 4 edges, then I think I don't remember this exact question. I think in this question we are asking at most 3 edges. I think with at most 3 edges, because actually you will have to do manually. See, okay, are you getting my point? See, you will have to do this manually. This is what I am saying. I am saying that you will have to do this manually. So what you can do in this question, what you can do, you can just simply assume that with at most 3 edges, because you will have to do manually. So so definitely this will take a lot of time. Okay, so that is the reason in the GATE exam they will give you very small data. See, one thing I want to tell you, there are some problems, there are some combinatorics problem, some mathematical problems which will take a lot of time if you solve them for big values. Okay, so for big values of n, for big values of I can say input, if you solve them, then they will take a lot of time because there is no direct formula. There are many problems, many mathematical problems, they do not have direct formula. Okay, so that is the reason if you solve them for large values of input, then they will take a lot of time. Okay, so that is the reason in the GATE exam, if they ask you some question from this type of problems, then they will give you small data. Okay, they will give you small data if they ask you any question from this type of problems. Like for example, number of unlabeled graph. Okay, how many unlabeled graphs are there? So again, this question, how many unlabeled graphs are there, this is not, I can say, there is no efficient formula for this. Okay, there is no direct formula or there is no efficient formula. So that is the reason, that is the reason I can say in this type of question they will ask you only for small data. Okay, so with at most 3 edges the answer will be what? With at most 3 edges the answer will be what? 1 plus 1 plus 2, that is 4. 4 plus 3, answer will be 7. So something like this you can do. Okay, so anyway, there are many questions in mathematics. Okay, in combinatorics, in counting, there are many questions which do not have any efficient formula, which do not have any direct formula. So for this type of questions, they will always give you small data, they will always give you I can say small values. For small values they will ask you. Okay, so that you can do it very easily, manually you can do it. Okay, now let's see this question. This is interesting question, this is very interesting question. So let's solve this. During the GATE exam, how will you solve it? See, I will give you the complete analysis, but during the GATE exam, how are you going to solve this question? Okay, see, in the GATE exam, during those 3 hours, in those 3 hours, how will you solve this question? This is GATE 2004 question. The question is asking how many graphs on an labeled vertices. The question is saying labeled vertices. Okay, how many graphs exist which have, by default graph means simple graph. Okay, remember this point. By default, I told you by default graph means simple graph. So how many labeled graphs are there on n vertices which have at least these many edges, which have at least these many edges? So tell me, in those 3 hours, how are you going to solve this question? In those 3 hours, this question, how will you solve in those 3 hours? Tell me. So you can notice this is in those 3 hours, in those 3 hours of GATE exam. So during the GATE exam, how are you going to solve this? Then we will see the complete analysis. Don't worry. We will also see the complete analysis, but let's see this. So during those, so tell me, what are you going to do for this question? You can take a small value, right? Okay, you can take a small value, you can take. So let's assume that you take n equal to 3. Okay, let's see. Maybe you can take n equal to 4 also you can take, but you can take a small value. Okay, so let's take n equal to 3. Then for this n equal to 3, you tell me how maximum how many edges you can have. Tell me what is the number of edges we can have. Can you tell me what is the number of edges we can have? Number of edges we can have. Number of edges that we can have is 0 to, number of edges that will be 0 to nc2, where n is equal to 3. So that will be like, I can say number of edges will be 0 to 3. Okay, so 0 to 3 edges you can have. Now what the question is saying? The question is saying that at least these many edges must be there, n square minus 3n by 2. But the question, what the question wants, what the question is wanting, okay, the question is saying that at least n square minus 3n by 2 edges, at least these many edges. So what is this value? First of all, like n square, that is 3 square, 9 minus, okay, so n square 3 into 3. Okay, so that actually that will be 0, at least 0 edges. Okay, so I think here we will not be able to do anything because the now ultimately this is like, so the answer will be what? Just tell me. In this situation, the answer will be what? In this situation, the answer should be what? At least 0 edges should be there. So the answer will be what? The answer will be 2 power nc2. The answer will be 2 power nc2, or I can say 2 power 3. 2 power 3. Okay, So the answer will be this. The answer should be 8. The answer should be 8. So which formula is given, which is giving you when n equal to 3, then answer should be 8. Then answer should be 8, which is giving you 8. Like, can you check which is giving you 8? So for example, what this option A is giving you, look at this. What this option A is giving you, this is giving you 3c n square minus 3n by 2, that is 0. So 3c 0, that is 1, right? Okay, so this gone, correct? This option is gone, yes or no? Right, yes or no? So this option is gone. Okay, what about let's see one by one. Let's see one by one which options are gone. Let's see this option. Option C, n square minus n by 2. So this is 3 c 3c n is equal to 3. So that is also gone. Option C is also gone. What about option B? What about option B? Tell me. What about this option B? Like, look at this option B and tell me. So this option B is saying that summation from k equal to 0 to 0. Okay, so summation from k equal to 0 to 0. Okay, so that is n square minus n. So that is 9 minus 3. Okay, so 6ck from 0 to 0. So that is like 6c0, and that is also gone. This option is also gone. Look at this option D. What this option D is saying? This option D is saying that summation from k equal to 0 to n is 3. So such that this value, what is this value? N square minus, okay, 3c k. Yeah, this is correct, right? Yes or no? Because this will give you 3c0 plus 3c1 plus 3c2 plus 3c3, and that is your 2 power 3. Okay, and that is 8. So the answer will be 8. So tell me, in the GATE exam, how much time it will take? Tell me. During those 3 hours, I am telling you during those 3 hours, in those 3 hours of GATE exam, how much time it will take? Like, you can get the correct answer. Just take n equal to 3. This n equal to 3 you take, and you can get the correct answer immediately. The answer will be option D. Option D answer you can get, right? Yes or no? So during those 3 hours, you can take maybe during those 3 hours, maybe you can take n equal to 3, or maybe you can take n equal to 4, and you will get your answer. Okay, get answer, and that's it. Because in those 3 hours you can do this, right? Yes or no? And okay, get answer, get 2 marks. But tell me, will you be satisfied by this method during your preparation? Like, when you are preparing for the GATE exam, during the preparation, will you be satisfied with this method? Should you be satisfied with this method? Will you feel satisfaction with this method? This is a nonsense method, right? Yes or no? Do you agree with me that in those 3 hours you can do this? In those 3 hours you should do this. Okay, in those 3 hours you must do this. I can say in those 3 hours you must do this. It will save you a lot of time. Okay, a lot of time you can save. But during the preparation, will you be satisfied by this method? This is a nonsense method, let me tell you. Like, this is a typical coaching method. In most of the coaching institutes, the teacher will tell you this type of method. Okay, and the students will feel very happy. Okay, because they are getting the answer immediately. For a GATE question, within 1 minute they are getting answer. So the students will feel very happy. But the students are not learning anything. During the preparation, if you are solving like this nonsense method, if you are applying, then definitely this will not improve your knowledge. Because maybe in the GATE exam, maybe they can give you NAT. Then how will you do? Yes or no? In the GATE exam, if they give you NAT, numerical answer type, then how will you do? So remember, this method is fine for those 3 hours. This method is fine, but this is not complete analysis. So let's start with our complete analysis. Okay, one thing I know, look at the options. What these options are telling you, the answer should be in what format. Look at this. These options will give you some idea. The options are giving you some idea. Tell me, definitely answer is in the format of C, right? Yes or no? Definitely answer is a single term, right? Yes or no? In in form of in form of YCX. Yes or no? Okay, correct. There is a single term. So definitely, like, the question is asking for at least. So definitely there will be a series. Do you agree there will be a series? For example, let me give you, before we see the complete analysis, let's assume n is equal to 4. So what this question is saying? This question is saying that what this question is saying, the question is saying that you want at least number of graphs with at least how many edges? At least n square minus 3n by 2, these many edges. So n square minus 3n by 2. Okay, so tell me what is this? N equal to 4, then that will be 2, at least 2 edges. Yes or no? The question is asking that at least 2 edges must be there. Then your answer will be what? If you want number of graphs with at least 2 edges, number of graphs, labeled graphs, okay, number of labeled graphs with at least 2 edges, with greater than or equal to 2 edges, then you will get a sequence, you will get a series, right? Yes or no? So you are going to get a series. This series you are going to get, you will get, for example, maybe 2 edges or 3 edges or 4 edges or 5 edges. Maximum how many edges you can have? If you have n equal to 4, then maximum 6 edges you can have, right? Maximum nc2, which is 6 edges. Maximum these many edges we can have. Okay, so you will get a series, number of graphs with greater than equal to 2 edges. Then what your answer you will get? Number of edges can be 2 or 3. Number of edges, that can be 2, or that can be 3, or that can be 4, or that can be 5, or that can be 6. Okay, so first of all, like 16 minus 12, yes, that is 2 edges. Okay, so you can notice that either 2 edges, 3 edges, or 4 edges, or 5 edges, or 6 edges, these many edges you want. Okay, and the question is asking for how many graphs are there, number of graphs. So tell me how many graphs with 2 edges. For this, how many graphs with 2 edges? How many graphs we have with 2 edges? There are 2 edges. How many graphs with 2 edges? Tell me. Like, simple question I am asking. If I ask you this question, that this is your question, let's assume you have n vertices. Okay, how many graphs? Number of simple graphs and labeled vertices. Okay, so let's assume you have n labeled vertices, and I am asking number of graphs with 3 edges. Tell me what that will be. Tell me what is that will be. What that will be? Number of graphs, labeled vertices, you have n labeled vertices with 3 edges. So you can notice you want to select 3 edges, right? Yes or no? You just need to select 3 edges. Very good. Correct. See, total maximum, like I can say maximum nc2 edges are maybe possible. nc2 edges possible. Maximum these many edges are possible. Maximum these many edges possible. But how many I want? I want 3 edges, right? Yes or no? So from these I need to select 3 edges. That's it. From these nc2, let's assume from this nc2 I need to select 3 edges. The answer will be this. Yes or no? I need to select 3 edges. Correct or not? I want 3 edges. These are the number of pairs. This is the number of pairs of vertices. Okay, this is the number of pairs of vertices. These many pairs of vertices are possible. I want only 3 edges. So I will select 3 pairs. And I will put edges. Correct or not? I will select 3 vertices. I will select 3 pairs and I will put edges. These many maximum edges are possible. From these edges, I will select 3 edges. That's it. Yes or no? Similarly, for example, if I ask you how many graph with k edges possible, then the answer is what? Then the answer is nc2. From nc2, I can select k edges. This will be your answer. Correct? Yes or no? Very simple. So how many graph with k edges are there? So the answer will be nc2ck. So here you can see that how many graphs with 2 edges. So let's assume this nc2 for a moment. Let's assume this nc2 is equal to some quantity. Let's assume this nc2, what I'm saying, let's assume this nc2 is equal to a. This nc2 is equal to a. For a moment, let me assume nc2 is equal to a. Then here answer will be ac2 plus ac3 plus ac4 plus ac5 plus ac6. Do you agree? Do you agree that answer will be this? Yes or no? Okay, correct. AC2. Okay, from these many edges are possible. Maximum these many edges are possible, but I only want two edges. These many pair of vertices are possible. Okay, these many pair of vertices are possible, but I want two edges. So what I will do, I will select two pair of vertices. Similarly, or I can say, or you can understand like this: these many edges are possible, maximum these many edges are possible, but I only want two edges. So from these edges I will select two edges. Okay, or from these edges I will select three edges, and so on. AC2 plus AC3 and so on. This is your answer. So tell me, what is this one? Like, you got this. What you got? If you have n equal to 4, then number of graphs with at least two edges. With at least two edges. What is that? That is your AC2 and so on, AC6. And what is that? AC2, AC6. What is that? Remember, what is A? A is already 6. Correct? A is already NC2. A is already 6. So A is already 6. This A, this already is 6. So 6C2 and so on, 6C6. Okay. What I can do? See, what I can do, I can write like this. This 6 NCR is equal to NCN minus R. Correct? Okay. So we already know that NCR is equal to NCN minus R. So using this, what I can do, I can say that 6C6 is equal to 6C0. I can say 6C2 is equal to 6C4. Okay. So what I can do, I can write it 6C0 plus 6C1 and so on till how much? Till how much? 6C4. Yes or no? 6C4. This is what I will get. Now what is this value? This value is summation of A, C, K, where K is going from where? K is going from 2 to, sorry, K is going from 0 to N. This 4 is N, right? Yes or no? This 4 is N. So this K is going from here to here. This is your answer. So what is the answer? The answer is quite simple. So what we got, remember, from this analysis, you got this answer. So what is the answer that you understood? So finally, I can say that that I can say, if you have n vertices, if you have n labeled vertices, okay, then number of graphs with at least n square minus 3n by 2 edges, the answer will be what? The answer will be summation K is going from 0 to N. Okay, that A, C, K. What is A? What is A? A is NC2, which is nothing but n minus 1 by 2, which is nothing but n square minus n by 2. So your answer will be what? Your answer is going to be what? The answer will be option D. Okay. So this is your analysis. But again, this is not a complete analysis, because remember, I have taken this case. I have taken n equal to 4, right? Yes or no? I have given you n equal to 4, but you understood the idea. I only wanted to tell you the idea. Tell me, so far, is this clear? So far, did you understand? Please tell me. So far, at this point of time, did you understand? Let me know. Okay. Now let's see the general. Okay. So let's do. I can say general derivation. Let's do the general derivation. It will actually. This general derivation is not interesting. This is just manipulation. It will not improve your knowledge, but it is just manipulation of quantities. Okay, this general derivation that we will see, it is not going to, you will not feel that this is a very, like I can say, logical derivation. This is not a logical derivation. This is just, I can say, this is just a manipulation. Okay, we are just manipulating the quantities. So what is general derivation? So you have n labeled vertices. The question is saying that there are n labeled vertices. Okay, and what we want, we want at least, this is what we want at least n square minus 3n divided by 2 edges. This is what we want. Okay, and total maximum how many edges we can have, tell me. Okay, so let's assume a is equal to nc2, which is nothing but n square minus n divided by 2. Okay, so let's call it a, and let's call it b. Okay, so you are calling it a, you are calling it b. Now let's see, so what your answer will be. So finally I can say either you have b edges at, we want, what we want, tell me what we want greater than equal to b edges, correct? Yes or no? Greater than equal to b edges we want, correct? Okay, maximum a edges we can have. So we want greater than equal to b edges, maximum a edges we can have. This is the maximum number of edges we can have. So I can say this is your maximum number of edges we can have. So this a is the maximum number of edges, and at least b edges we want. So you, what your answer will be, either you have b edges, or you have b plus 1 edges. Okay, or you have, and so on, finally you have a edges, correct? Okay, finally you have these many edges. So tell me how many graphs with b edges, tell me how many graphs we have with b edges. So for b edges, how many graphs we have? So maximum these many edges you have. Okay, you can notice that maximum, I can say C, maximum these many edges you have, and you select b edges, plus maximum these many edges you have, select b plus 1 edges, and so on. Maximum these many edges you have, select a edges. This is your answer. Very simple, right? Yes or no? This is extremely simple, that this will be your answer. Okay, your answer is going to be this one. This is the answer. But how to convert this into a single quantity, right? Yes or no? See, this is your answer. There is no problem. This answer is correct. There is no problem. This answer is absolutely correct. But how to convert this into a single quantity? Okay, so from a you are selecting b edges, from a you are selecting b plus 1 edges, and so on, a edges. So how to convert this into a single quantity? Then what you can do, again you can use this rule. This rule you can use. This is very useful. So you can notice AC B plus 1, and so on, ACA. So what you can do, you can convert this into this type of series, like AC0, AC1, this type of series you can convert. So what you will get, tell me, ACB plus ACB plus 1 plus ACB plus 2, and so on. Ultimately you are getting ACA. Just before that, what you are getting, you are getting ACA, just before, like, okay, and so on. So just before that, like we are increasing, so just before that you are getting ACA minus 1, right? Yes or no? Just before that, because we are increasing. So now what you can do, you can use this rule. This rule you can use, NCR is equal to NCN minus R, correct? This rule you can use. Just use it. If you use it, then this will become what? Tell me. This will become what? So this will become AC0 plus. Okay, this will become AC0 plus. This will become what? This will become AC1 plus, and so on. Ultimately you will get what? ACA minus B. Can you tell me what is A minus B? Like, what is A minus B? See, A is this, NC2. A is n square minus n by 2. And what is B? Tell me what is B? B is n square minus 3n by 2. What is A minus B? Tell me what is A minus B? So if you, from this, if you remove this, then what you will get? You will get 2. From this you remove this value. From this, if you remove this value, you will get 2. N square minus n square plus 3n. So what you are getting? You are getting n. Okay, beautiful, right? Yes or no? Beautiful, because ultimately we got n. Ultimately we got n. Ultimately this is equal to n. So what we got? Tell me your final answer. You got your final answer, that is AC0 plus AC1 and so on, ACN. ACN, and that is nothing but summation. A is fixed. This A is fixed. Okay, ACK, this K is going from 0 to n. And what is this A? This A is n square n minus n by 2. That's it. Please tell me, did you enjoy? Let me know. The complete analysis, did you enjoy? Let me know. Okay. See, this will not be 2 power A. Please understand that this will not be 2 power A. This will be 2 power A if you go till last. This will be 2 power A if you go till A. See, if you go till A, then this will be 2 power A. Then this will be 2 power A. But we are going from AC0, we are going till n only. We are going till only n. Okay, we are only going till n. So that is like summation. A is fixed. A is fixed. This K is going from 0 to n. Please tell me, did you enjoy this proof? The complete analysis, did you enjoy? Let me know. 3 methods I told you. How to solve in the GATE exam, I told you. I told you if you take n equal to 4, I told you. Okay, n equal to 4. With n equal to 4, you can understand. Or if you want the general proof, you can do that. Please tell me this question and the complete analysis of this question, did you understand? Let me know. Let me know. Understood? This was your question, a beautiful question from GATE to 2004. Okay, a very nice question. During those 3 hours, how can you solve? In those 3 hours, you can take n equal to 3. If you take n equal to 3, then you can remove A, B, C. Option A, B, C you can eliminate. Answer will be option D. So during those 3 hours, you can get marks. You can get 2 marks. You can immediately get. Okay, you can immediately get 2 marks in the indoors. But remember, let's do the complete analysis. Then you can notice that if you take n equal to 4, then answer will be, you want at least 2 edges. Okay, so either 2 edges or 3 edges or 4 edges or 5 or 6. So your answer will be AC2 plus A and so on. So you can just check it out. Okay, similarly you can do the general solution. If you want this general solution, you can get it. Okay, you can do it. So your answer will be what? This quantity is A, this quantity is B. Your answer will be ACB plus ACB plus 1 and so on. You can use this formula, and if you use this formula, that's it. A minus B is equal to N, that's it. Okay, so let me know. Should I move on? Should I go to the next question? Please tell me. This question is clear, right? Yes or no? Beautiful question. The complete analysis we have done. Niranjan is asking, sir, what about unlabeled variation for this question? Is it possible? Of course it is possible, Niranjan. Of course that is possible, but that will be time taking. Okay, as I told you, unlabeled variation, that is time taking. There is no direct formula. There is no efficient formula. Okay, if there is a formula, that is very complicated. Okay, the formula will be very complicated. Okay, so for there are some problems, remember, in mathematics, in computer science, in any field, in combinatorics also, there are some problems. There are some counting problems which are, I can say, which don't have efficient solution. So for example, number of equivalence relation, yes or no? If I want to ask you how many equivalence relations are there, if I want to ask you how many number of equivalence relation, if I want to ask you, then there is no efficient formula. In the GATE exam, they will ask you n equal to 4, n equal to 5. They will never ask you n equal to 8. They will never ask you that how many equivalence relations are possible on a set with 8 elements. They will never ask you. Those professors are not dumb. Okay, those professors, these are IIT, IISc professors, they are not dumb. They know which problems you can solve. Okay, which problems have efficient mechanism and which problems do not have efficient mechanism. Okay, so don't worry about it. Is this clear? Please let me know. Okay, clear? The previous question is clear, right? Yes or no? Okay. So now let's move on. Now let's see this. Okay. So let's move on to the next question. This is actually uh, Go classes test series question, but I wanted to take this question because this is another standard question, a very nice question. So read this question and tell me the answer. This is Go classes test series question. Go classes discrete mathematics test 5. Okay. Go classes test series discrete mathematics test 5 question number 17. So try this question. Try this question. So the question is actually very simple. So I am giving you take 1 minute, 2 minute you take and try this question. Okay, you have 2 minutes. Try this. Hi everyone. Did you try this question? Let me know. Are you working it? Please tell me. Are you still working it or should I tell you the solution? Are you trying or should I tell you the solution? Let me know. Okay. So you can try if you are trying. Okay, if you are working this question, working it out, then you continue. Okay, but also listen to my solution. I am providing you the solution now, so listen. Okay, trying. Okay. Okay, Rohit and Akash, they are saying trying. Okay, so take 1 minute. Okay, I am also waiting. Ankit is saying 1024. Ankit, I don't know the answer. I will also have to check it. Ankit, can you tell me the idea? So Rohit is saying 4096. Okay. So I don't know the answer. I will have to try. See, for the last 2 3 days, I have been sick. So that is the reason the voice is maybe the voice is different. Okay. So but don't worry about the voice. Ignore the voice and just focus on the complete analysis because only the voice is different. everything else is same, my energy is same. Okay, my intention to provide you complete analysis, that is same. For every question I will provide you complete analysis with variations, because the gate exam is all about understanding. Gate exam is all about understanding the complete analysis of questions. Okay, now let me try. Okay, so just wait. What the question is saying, read the question. So the question is saying that there is the definition of simple graph is given to you. A simple graph is undirected graph in which each edge will connect to different vertices. No two edges connect the same pair of vertices. This is the usual definition, right? Yes or no? Do you agree this is the usual definition? Each edge will connect to different vertices. It means there is no self loop, correct? Okay, so what it means, each edge connects to different vertices. What it means, it means no self loop, no self loop. And the question is saying no two edges connect the same pair of vertices. It means no multi edges, right? Yes or no? It means no multi edges. There is no multi edges, no multi edges. This is the usual definition. Do you agree? Okay, the first line is clear. Tell me, the first line is clear. This is the usual. This is the usual definition of simple graph. We already know. Okay, we already know this definition of simple graph, undirected graph. Okay, now what the question is saying? The question is saying an oriented simple graph. Oriented simple graph is a simple graph which has been converted to directed graph by assigning an orientation to each edge. Okay, to every edge we are giving assignment, we are giving direction. The orientation of u comma v can be thought as a mapping to either uv or vu, but not both. Okay, so for example, if you have this, basically you cannot have both of them together. Okay, either you will put direction from u to v, or you will put direction from v to u, but you will never put direction in both the sides. Okay, you will never put direction in both the directions. Okay, now the question is asking, what is the number of oriented simple graph on 5 vertices? On 5 vertices, how many oriented simple graph? Did you understand the definition of oriented simple graph? See, first of all, simple graph is given to you. The question is saying that what is simple graph, that is given to you. Now, what is oriented simple graph? Oriented from this simple graph, like for example, consider this simple graph A, B, C, D. Consider this simple graph. Now you can notice this is a simple, graph, right? Okay, this is a simple graph, or maybe you can take this. So this is simple graph. Now what you are doing, you are converting this into oriented simple graph. Okay, this oriented simple graph, you are converting this to oriented simple graph. You are giving direction to every edge. Okay, you are giving direction to each edge. You are giving direction to each edge. Okay, so to every edge you are giving direction. Like these are the edges, right? Yes or no? A, B, C, D. These were the edges. These were the edges. To every edge you are giving direction. But the question is saying that either if you have this edge, then either you can give this direction from u to v, or you can give from v to u, but not both. Okay, so if you have this edge, for example, this edge you have, so either you can give the direction from a to b, or you can give direction from b to a, but you cannot do this. This is not allowed. This is not allowed. Okay, this is not allowed. Is this clear? This is not allowed. So I can say that either you can give this direction. To every edge you are giving direction. Okay, but only one direction you can give. To every edge you can give only one direction. To every edge you can give only one direction. So this is your oriented simple graph. Now the question is asking, what is the number of oriented simple graphs? What is the number of oriented simple graphs? What is the number of oriented simple graphs? How many oriented simple graphs you can create? If you have 4 vertices, like for example, look at 4 vertices or maybe n vertices. You have total n vertices. Okay, total you have n vertices. You tell me a simple point I'm asking, a very simple question I'm asking. For any pair of vertices, how many choices you have? A simple question I'm asking. For any pair of vertices, how many choices you have? For any two vertices, like for this pair of vertices, how many choices you have? Tell me. For this pair, for this pair, how many choices we have? Can you tell me how many choices are there? Please tell me. For this pair, how many choices are there? There are three choices, right? There are three choices. Either you can put this, or you can put this, or you don't put anything. For example, there is no age between C comma D. There is no age between C comma D, right? There is no age. There is no age between them. There is no age between them. So there are three choices. Do you agree that there are three choices? Okay, what are these three choices? What are these three choices? These three choices are either you put from A1 to A2, or you put from A2 to A1, or you don't put no age, or if there is no age. So these are the three choices. Okay, so for every pair of vertices, there are three choices. Now you tell me the answer. So for every pair of vertices, so for every pair of vertices, for every pair of vertices, tell me how many choices? For every pair of vertices, there are three choices. There are three choices. So the answer will be what? So the answer is going to be, for every pair of vertices, how many pair of vertices are there? How many pair of vertices? NC2 pair of vertices. Pairs of vertices. How many pairs of vertices? For every for every pair you have three choices. For every pair we have three choices. So the answer will be 3 power NC2. N is equal to 5. Now you can put n equal to 5. Okay. So please tell me, did you understand this question? Did you understand the solution? And did you like the question? Please tell me. Okay. So for n equal to 5, what will happen? You can calculate. For n equal to 5, the answer will be 3 power 10. 3 5 C2. That will be 3 power 10. You can calculate with calculator. With calculator, you can calculate. In the GATE exam, there is calculator. You can calculate. Okay. Please tell me, did you understand? Did you completely understand this question? Okay. The question is very simple. The question is saying that basically you don't have, in both direction you don't have. This is same as number of asymmetric, right? Did you notice this oriented simple graph? Did you notice this oriented simple graph that we have defined in previous question? In previous question is same as asymmetric relation. Asymmetric relation graph. Asymmetric relation graph. Yes or no? Is same as asymmetric relation graph, because you don't have any self loop. Okay. Because it is not self loop. There is no self loop, and you do not have this type of edges. At most one edge you can have between any pair of vertices. Okay. So this is same as asymmetric relation graph. Okay. So that is the reason you can see the answer is 3 power NC2. Okay. I hope you understood this point. 3 power NC2. Okay. 3 power NC2. Okay. So very simple. Now let's move on. So this is a Go classes test series question. So in the Go classes test series, actually, I just want to tell you, because if you have not if you have not given any test from the Go classes test series, then in the Go classes test series you will find well framed. First of all, did you notice this question is very well framed? Every information is given to you. There is no ambiguity. Yes or no? In this question, there is no ambiguity. It is a well framed question, standard question, okay, and original question. Okay, so you can see that in the Go classes test series, you will find this type of, I can say, gate worthy questions. Okay, now let's move on. Now let's see some TIFR questions. Because TIFR also, this is a brilliant exam. In this TIFR, a lot of good quality questions are there. So let's see this. Let's see this question. Quickly tell me the answer. Tell me the answer now. So what is the answer? In a graph, this is TIFR 2012 question. In a graph, the degree of a vertex is the number of edges incident on it. Okay, the degree is the number of edges incident on it. That is fine. Your usual definition, right? Yes or no? This is our usual definition, standard definition, correct? This is the standard definition of degree. Okay, now which of the following is true for every graph? Which of them is true for every graph? So the answer is, we already know the answer is, there are even number of odd degree vertices. There are even number of vertices of odd degree. So the option C will be correct. This we have already seen in the last session. In the last video, in the last lecture, we have already seen this. So the answer will be option C. But you tell me which of them is never true. Which of them is never true? See, answer will be option C. But you tell me which of them is never true. Never. Which of them is never true? So you can notice this is never true. There are odd number of odd degree vertices. This is never true. This is never true. Correct? All the vertices of even degree. All the vertices are of even degree. This may or may not be true. This may or may not be true, right? This may or may not be true. But remember, option D is never true. Okay. What about this? Even number of even degree vertices. Again, this is again may or may not. Again, this is may or may not. Again, this is may or may not. Okay. So the answer is very simple. The answer will be option C. Option C is always. Option C is always true. This is always true. Okay. Option D is never true. Option A, B, E, these are may or may not be true. Let's move on. Now I am asking this question. First of all, you tell me, is this true or false? Is this true or false? A simple question I am asking. Is this statement, look at this statement, true or false? This statement on your screen, this is true or false? In any simple graph, there is a path. There is a path from any vertex of odd degree to some other vertex of odd degree. Is this statement true or false? In any simple graph, whatever simple graph you take, there is a path from any vertex of odd degree to some other vertex of odd degree, to some other vertex of odd degree, to some other vertex of odd degree. Is this statement true or false? Why this statement is true? Yes, this statement is true, but why? This statement is true, but what is the proof? Ankit, what is the proof? Like, why this statement is true, that if you have odd degree vertex, for example, if this is a odd degree vertex, if this is odd degree vertex, then definitely there will be a path to some other odd degree vertex. This is A not equal to B, and this is odd degree vertex. There will definitely be a path. Why this statement is true? Can you tell me? What is the proof why this statement is true? This statement is true. You can take any odd degree vertex. This can be any odd degree vertex. Okay. Then to some other odd degree vertex, there will be a path. Why this statement is true? The statement is actually true. The reason is very simple. Because tell me, simple question. Array, if you take a component, okay, a simple question I am asking. Just take any component. Take a connected component. What will happen? Take a connected component. What will happen in this connected component? Tell me. Can I say this connected component is also a graph? Can I say? Can I say that this connected component itself is a graph? Can I say this connected component itself is a graph? Itself is also a graph. Is also a graph. Right? Correct? Like if you have connected component in any graph, so you have a graph. Let's assume you have graph G. In this you have connected component C1. Okay, this is your connected component. This is your connected component C2. Okay, so this C1 means connected component. This is connected component. This is your C1, this is your C2, and so on. So can I say that this itself is a graph? Yes or no? This is also a graph. This is also a graph individually. Individually, this is also a graph. Individually, a graph. Individually, also a graph. Yes or no? This is a graph. This is a graph. So what should happen? If this connected component is also a graph, then what should happen? Then this would happen that in this connected component, number of odd degree vertices, how many should be there? Tell me. Then how many should be there? So in this connected component, this is your connected component. How many odd degree vertices must be there? Tell me. How many odd degree vertices must be there? So there should be number of odd degree vertices. How many? Number of odd degree vertices. That should be even. That should be even. Correct? Yes or no? Array, this is also a graph, right? Take any connected component. This component is also a graph. This is also a graph. This is a graph. This component itself is a graph. Correct? This component, this is a graph, right? Yes or no? Now you can notice that. Look at this component. For example, this component. Look at individually. Look individually. This is a component. This is a graph. Individually, these are graph. Like I can say individually. Look individually. Individually, this is a graph. Individually, this is a graph. Now you can notice there should be even number of odd degree vertices. That's it. This is your proof. So now you tell me, array, if you have any odd degree vertex, if you take any odd degree vertex, then what will happen? If you have any odd degree vertex A, then what will happen? It will belong to some component. Do you agree? It will belong to some component. Yes or no? It belongs to some component. Definitely. It belongs to some component. Can I say? Can I say it will belong to some component? Yes. So it will belong to some component. Then in this component, there will be another even number of odd degree vertices. Yes or no? So there will be another odd degree vertex. Definitely. So in this component, there will be another odd degree vertices. So in this component, there should be, there must be even number of odd degree vertices. Odd degree vertices. Okay, so there will be another odd degree vertices, definitely at least one. Yes or no? Correct? Array, this is already odd degree vertex. This is already odd degree vertex. There should be another, because there must be even number of odd degree vertices. This is one, so there should be at least one more. At least one more. Maybe 3, maybe 5, maybe. Okay, so there can be number of odd degree vertices can be 2, 4, 6. Okay, so there should be another. There should be some odd degree. This should be, I can say this must be some odd degree vertex. This must be some odd degree vertex. And because they are in the same component, because this is a component, by the definition of component, what will happen? By the definition of component, what will happen? By the definition of component, they will have a path. Yes or no? By definition of component, they will have a path. By definition of component, yes or no? The component definition tells you that there is a path. Okay, because component is connected, right? Because component is connected. Okay, so that is the reason by the definition of component there is a path. So is this clear? Interesting, right? Yes or no? See, this same statement we are saying in another way. Did you notice this same statement? Look at this. Look at this option number C. This same statement we are saying in another way. Forget about remaining options. Look at option number C, and this option number C we can say in another way. Correct? Okay. This same statement we are saying, this same statement we can rephrase in many ways. Can rephrase, remember, we can rephrase this statement. Can rephrase in many ways. Okay, is this clear? Please tell me, did you understand? This same statement you can rephrase in many ways. This is one of those. Like I can say that in any simple graph, okay, in any simple graph, there is a path from any vertex of odd degree to some other odd degree vertex. So this statement is true, correct or not? Please tell me, did you get it? Like any odd degree vertex, there will be a path to another odd degree vertex because in a component you must have even number of odd degree vertex. In any component you must have even number of odd degree vertex. So that is the reason I can say, by the definition of component, I can say that this must be true. This statement must be true. Correct or not? Okay, so this we have proven. What is another way to say this same statement? This same statement, this option number C, you can rephrase it in many ways. What is another way? What is another way? Let me give you another way. Let me give you another way. This is another way. Read this question. Is this true? Read this question. If a graph has exactly two vertices of odd degree, if a graph has exactly two vertices of odd degree, they must belong to same component. Is this correct? Is this true? If a graph has exactly two vertices of odd degree, graph has exactly two vertices of odd degree in your graph, in the entire graph, like let's assume this is your graph, this is your graph G. In this graph G, if you have two vertices of odd degree, exactly two vertices, let's assume like A comma B, these are the two odd degree vertices, then can I guarantee they must be in the same component? Can I guarantee they must be in the same component? Of course. Of course, it is not possible, right? Like A is here, B is here. This is not possible, correct? This is not possible because in this component you must have even number of odd degree vertex. Correct? Yes or no? In this component, how many even degree vertices you must have? In this component, you must have even number of odd degree vertices. So this is definitely not possible. Okay, this thing is definitely not possible. So if this is not possible, then what we can say? We can say that they must be in the same component. If they are in the same component, then there will be a path. Then there will be a path. Okay, then there will be a path. Then there will be a path. That's it. Okay. So did you notice the same statement you can rephrase in many ways? In the GATE exam, this same statement they can ask you in many ways. This is the beauty of GATE exam, right? Yes or no? This same statement can come in many ways. Okay, remember this same statement can be asked in many ways, in several ways. So you tell me a simple thing. Will you be able to solve in several ways? In several ways. Some of them I have already told you. Some of those I already told you. Is this statement true? Look at this statement. Is this statement true? They are connected by age. Is this statement true? They are connected by age. Is this statement true or false? They are connected by age. You have exactly two vertices of odd degree. They are connected. They must be connected by age. Is this statement true or false? Exactly two vertices of odd degree. They must be connected by age. Is this true or false? This statement is false. This is false. Very easy counter example you can give. Okay, very easy counter example you can give. Like here you can notice this is odd degree vertex, even degree, even degree, even degree, odd degree. So you can notice odd degree vertex, odd degree vertex. Okay, so this statement is definitely false. You can easily see this is the counter example. This is the counter example. Okay, so what I want to tell you, finally what I want to tell you, I want to tell you that these statements are true. Okay, then they belong to same component. This statement is correct, right? Yes or no? If you have only two vertices of odd degree, if you have exactly two vertices of odd degree, then they must belong to same component. Then they must be in same component. Then they must be in same connected component. This is true, right? Okay, so this is actually true. This statement we have already proven. Okay, if your graph, in this graph you have this is the graph. Okay, you have exactly two vertices of odd degree. So let's assume those vertices are a comma b. Then definitely they can never be like this. This is never possible. Okay, this is never possible. This is never possible. The reason is very simple. The reason is very simple because this is a graph. Array, look at this. This is a graph. Individually, look at this. This is a graph. This is a graph. This is a graph. So individually, these are graph. So individually, this must have even number of odd degree vertices. This must have even number of odd degree vertices. This must have even number of odd degree vertices. All of them must have even number of odd degree vertices. So if you have exactly two vertices, then they must be in the same component. Then they must be in the same component. So I can say they must be connected by path. So this statement is correct. So this is what I want to tell you. I want to tell you that this statement in every graph, there are even number of odd degree vertices. Okay, this statement, the same statement you can write like this. This statement, all are same statements. Please tell me, understood? These three are same statement. So actually, let me tell you, do you agree with me? I am telling you one thing. Do you agree with me that in the GATE exam, if this statement comes, if the first statement comes, many students will solve it? Yes or no? This first statement, if this statement comes, then many students will be able to solve it, right? Do you agree? Because many students, they already know this statement. They are already familiar with this statement. But in the GATE exam, if this statement comes or this statement comes, then the probability will decrease. Yes or no? Like for example, maybe 99% students will solve this. Maybe 70% students will solve this, and maybe I can say maybe 50% students will solve this. So do you agree with me that the first statement, second statement, third statement, these are basically same. The same statement, the same theorem you are writing in three different ways. Yes or no? The same thing, the same statement you are writing in three different ways, but you can notice that if this statement comes in the GATE exam, many students will be able to solve, but these statements, some students will not be able to solve. Okay, so actually what happens here, this is the problem, that what we know we can't apply. Yes or no? So you must be Renzo. You must be in the Three Idiots, this Amir Khan. So you must be Renzo of Three Idiots. Okay, हमने पढ़ा था, उसने अप्लाई किया. You must be this. Okay, this must be you. What you study, you should apply. This is what I want. Okay, so what you study, you should apply. This should be you. Okay, anyway, so let's move on. Let's see this question. Tell me the answer. Quickly tell me the answer for this question. This is TIFR 2018 question. A very simple question. Tell me the answer. TIFR 2018. Tell me the answer for this question. I want correct answer. Think about it and tell me. The question is in front of you. This is TIFR, Tata Institute of Fundamental Research. This is excellent institute. Okay, you should apply for this exam also. You should appear in TIFR exam also. This is brilliant institute. Okay, like Indian Institute of Science, IISc, CMI, ISI, TIFR. These are research institutes. Okay, these four institutes that I told you, these are research institutes. These are brilliant institutes. You should definitely attempt their exam. Okay, so let's see this question from TIFR. Tell me the answer. So the question is saying that in an undirected graph, okay, try this. Just take 1 minute and try this. I'm waiting for your response. Also, please like the session. Like and comment on the session. Okay. All these marathons, all these sessions that we conduct on our Go Classes YouTube channel, let me tell you, we don't waste your time. Did you notice? Like in many institutes, in many YouTube channels, they will waste a lot of time. Okay, in 2 hour of lecture, they will basically teach for half an hour and they will waste a lot of time. But okay, we will not do that. So please comment and like the session. Okay, you try this question. So what is the answer? So let's see. So what the question is saying. So the question is saying that there is undirected graph with n vertices. Vertex 1 has degree 1. These vertices have degree 10. Okay. And the degree of vertex n is unknown. Then first of all, can you tell me what will be degree of that vertex? Can you tell me? Can you tell me that there are n vertices? See, there is a graph. There is a graph and the graph is undirected graph. There are n vertices. In this graph, there are n vertices. These n vertices are like this: 1, 2, 3, and so on. N minus 1 n. These are the vertices. These are your vertices. Now the question is saying that this has degree 1. Okay, so let's see. This has degree. This is degree 1. This has degree 10. This has degree 10. All of them has degree 10, 10, 10, 10. This is unknown. Can you tell me what will be the degree of this n? Can you tell me what will be the degree of this n? Definitely odd, because number of odd degree vertices must be even, right? Definitely the degree will be odd. Okay, this degree must be odd. This degree must be odd. Now again you tell me, simple question I am asking. So can I say they must be in the same component? Can I say they must be in the same component? Like this vertex 1, is it possible Is it possible that vertex 1 is here and vertex n is here? Is it possible? Like let's assume this is a connected component. This is your C1, this is your C2. Okay, this is a connected component. Okay, so this is a connected component. This is also connected component. So is this possible? Is this possible? The answer is this is never possible, right? Yes or no? Because this has odd degree, this has odd degree, no one else has odd degree, right? Yes or no? Correct? This has odd degree, this has odd degree, no one else has odd degree, no one else. So that is the reason this is never possible, because look individually this is a graph. Here you must have even number of odd degree vertices, here you must have even number of odd degree vertices. So remember, here you must have even number of odd degree vertices, even number of odd degree vertices. You must have even number of odd degree vertices. Correct? Correct? Must have even number of odd degree vertices. So that is the reason this is never possible. Okay, this thing is never possible. That is the reason. Okay, so this I can say this is never possible, because no one else has odd degree. So this is never possible, because in this component you must have even number of odd degree vertices. So they must be in the same component. Finally, I can say they must be in the same component. So you can notice this is the component, this v1 and vn must be in the same component. If they are in the same component, then by the definition of component, what will happen? By the definition of component, what will happen? If they are in the same component, then by the definition of component, there is a path. By the definition of component, okay, there is a path. So there will be path between them, you can say. So finally your answer will be that there is a path between these. So that is correct. This statement is correct. There is a path. This is correct. Okay, the remaining are actually wrong. The remaining options are wrong. You can create counter example for the remaining options very easily. Okay, let's see this. Option B. Option B is saying, what this option B is saying? This is saying that there is a path from vertex 1 to each vertex. This is not necessary. For example, option B, counter example for option B. Let me take. Okay, let's take counter example for option B. Counter example for option B. So what is the counter example for option B? Option B is saying that, what option B is saying? This is saying that there is a path from vertex 1 to each of these vertices. To each of these vertices. So that is definitely wrong. Okay, what you can do, you can easily create a counter example like this. What you can do, just create like this. This V1 and Vn you connect. Okay, now this is degree 1, this is degree 1. And the remaining vertices like V2, V3 and so on, Vn minus 1. The remaining vertices. Okay, let's assume that the total you have, let's assume here you have, what you can do, if you have 11 vertices here, so like V12. So what you can do, you can take n equal to 13. Okay, take n equal to 13. You can take n equal to 13. Okay, so you can take n equal to 13. Then you can notice that now you can make a connected graph here. You can make a complete graph here. You can make a complete graph here. So all the conditions are satisfied, right? Yes or no? Correct? Yes or no? All the conditions are satisfied. Do you agree? All the conditions are satisfied because you have a complete graph. So this at degree 10. So you can notice this at degree 10, this at degree 10, everything has degree 10, 10, 10, 10, 10, 10. So all the conditions are satisfied. Do you agree or not? All the conditions are satisfied, but there is no path between these vertices. There is no path between V1 and all these. So this is the counter example for option B. Did you understand the counter example for option B? So option B is wrong. Option C is also wrong. Option C, that is also wrong. What you can do, you can connect counter example like this. Option C is also wrong. What you do, you take n equal to 12. Okay, and you make a complete graph of V2 to V12. You make a complete graph of V2 to V12. V2 to V12, you make a complete graph. So at this point of time, tell me what is the degree? At this point of time, what is the degree? What is the degree of this vertex? This vertex at degree 10. This vertex at degree 10. So every vertex at degree 10 at this point of time. So there is a problem here. So what you can do, but where is V1? So what you can do, you can put V1 here. Now you can notice, this will be degree 11 and this will be degree 1. Did you notice? This is the counter example for option C. For option C, this is the counter example. Is this clear? Let me know. Tell me, is this clear to everyone? So everyone has degree 10, 10, 10, 10. Everyone else has degree 10, 10, 10, 10. You can take n equal to 12. And you can see all the conditions are satisfied. This is odd degree. This is odd degree. Odd degree, odd degree. Okay, both has odd degree. So you can notice all the conditions are satisfied. But this is the counter example for option C. So option C is not correct. What about option D? The diameter of graph is at most n by 10. The diameter is at most n by 10. This same counter example will work. This same counter example will work. This is the counter example will work. Tell me for this graph, what is the diameter? Tell me what is the diameter for this graph? What is the diameter for this graph? Tell me. On your screen, this graph is there. What is the diameter for this graph? Let me know. This graph, this is complete graph. So the diameter of this graph will be what? That will be 2. From V1 to V2. From V1 to V3. That will be 2. So the diameter will be 2. But the option D is saying at most. Option D is saying at most n by 10. Option D is saying at most n by 10. But you can notice 2 is not less than this. 2 is not less than equal to this. Yes or no? Is this clear? So 2 is not less than equal to this. 2 is not less than equal to this. Is this clear to everyone? Because remember, because this option is saying at most n by 10. At most n by 10. At most n by 10. But you can notice 2 is not less than, so this is, you can see that. So definitely this is false. This statement is false. Automatically this statement is false. So the answer will be what? Answer will be only option A. So this option A is correct. This is the complete analysis of each option. I have given you complete analysis of each of option, like option B, option C, option D, each option complete analysis we have seen. Please tell me, is this question clear to you? Very beautiful question, right? Yes or no? In the TIFR exam. A simple question, a very nice, simple question. Okay, let's move on now. This is the last question for today. So try this one. So this question I am giving you as a homework. The solution I will upload. What I will do? This question in our discrete mathematics course, we have already solved it. So take this question as a homework. Okay, this is TIFR 2010 question. So please take this question as a homework. You can comment your answer. You can comment your answer. Okay, so just comment your answer. Okay, so this question you can take as homework. And what I will do, I will upload, what we will do, I will upload solution of it. I will upload complete explanation, or I can say complete analysis of this question also. I will upload complete analysis. Okay, so today you will find the complete analysis of this question. Okay, so don't worry, the complete analysis I will upload. Do not worry about it, but you try this question. Okay, this is your homework question. You can comment your answer. Take some time. Take some time and solve. I will upload complete analysis of this today. Okay, so this is enough for today. Thank you everyone. And see, tomorrow we have algorithm marathon, right? Yes or no? This is our schedule for marathon schedule. So this marathon schedule that you have, So in this marathon schedule, if you see in this schedule, tomorrow we have algorithm, right? Correct. Tomorrow we have algorithm. Tomorrow means 17th. Tomorrow means 17th January. So on 17th January we have algorithm. But actually what we will do, see, we will complete the graph theory, okay, and we will complete the transport layer. So that is the reason this algorithm marathon we will shift to 23rd January. What we will do, so the remaining graph theory, the remaining graph theory, the remaining graph theory and remaining compute network and transport layer. In the compute network, transport layer is remaining, right? Yes or no? Sachin was taking compute network and transport layer was remaining, correct? Yes or no? So remaining graph theory and transport layer, these will happen tomorrow. So this will be shifted. This algorithm marathon, it will happen. Okay, will happen. When it will happen? It will happen on 23rd January. After the All India mock test. Okay. After the All India mock test on 22nd January, there is All India mock test. Go classes All India mock test on 22nd January. This is free for all. 22nd January. Okay. So we have Go classes All India mock test 2. Of course, this is free for everyone. Okay. On the GATEOverflow website. On the GATEOverflow website. You can check it out. Okay. So what I'm saying that this algorithm marathon, this will happen on 23rd January, and tomorrow means 17th January, we will complete these topics. Okay. These topics we will complete. Okay. So basically whatever we are covering, we want to cover in a perfect way. Okay. We don't want to leave in between. Okay. This graph theory, I will complete this graph theory tomorrow. This transport layer will complete tomorrow. Okay. So that compute network and discrete mathematics are completely covered. The revision of discrete mathematics and compute network. Remember, operating system revision is already over. Okay. So this revision, operating system revision plus gate PYQs, this is already over. This is already over. This is already available. Already completed. On the Go Classes YouTube channel, you can find it. Okay. Is this clear? On Go Classes YouTube channel, you can find this playlist. This playlist you can find operating system revision. This playlist you can find on Go Classes YouTube channel. Okay. So this is already over. Tomorrow compute network will be over. What will happen? Tomorrow compute network will be over. Discrete mathematics will be over. And then on 18th January, we have theory of computation. Okay, we have theory of computation on 18th January. On 19th January, we have engineering mathematics. Okay, so like this. Okay, thank you everyone. Anyone has any doubt, let me know. Anyone has any doubt? Okay, so let me tell you that discrete mathematics, complete discrete mathematics is freely available on the Go Classes website. Okay, so this complete discrete mathematics course, all the lectures, every homework, every weekly quiz, everything. So the complete discrete mathematics and complete C programming course, these are freely available for all the learners on the Go Classes website. You can go to Go Classes website or app. Okay, you can download our app. So go to Go Classes website, or you can download our app and you can study this. You can study complete discrete mathematics. You can study complete C programming. These two you can study completely. Okay, so remember, C programming and discrete mathematics, these complete courses are freely available for all the students. Okay, freely available on the Go Classes website. So you can study these two subjects. These two subjects you can study from Go Classes. Okay. So tomorrow we will continue this graph theory. So what we have done, actually, let me tell you what we have done. We have done these questions. We have done these questions, and some of these questions, some of these. some of these, some. Okay, so these things we have done. Tomorrow we will do coloring. This coloring we will do these things like planarity. Okay, so these remaining things we will do tomorrow. Okay, remaining tomorrow. Tomorrow means 17th January. Okay, so tomorrow we will do the remaining. If you want to download annotated notes, many students are asking for annotated notes. So where can you download annotated notes? Let me tell you, you can download annotated notes on the Go Classes website or app. On the Go Classes website or app, you can download these annotated notes. All you have to do, go to the Go Classes website. Okay, sign up for free, sign up or login for free. Then click on My Courses. When you click on My Courses, you will find this course. This course you will find. This is accessible to everyone. Okay, everyone has access of this course. So you will find this course. In this course, you can find the discrete mathematics, and there you can download the annotated notes. Okay, you can download the annotated notes. So if you want to download annotated notes, this is what you have to do. Okay, this is free for everyone. Just sign up, go to My Courses. You will find this course. In this course, you will find the annotated notes. Today I will upload, don't worry. Okay, today you will get these annotated notes here. Subscribe to the Go Classes YouTube channel so that you can get latest notification, all the latest video, all the latest lectures. Okay, you can get notification of that. So subscribe for the Go Classes YouTube channel, and also yeah, okay, so you can just check it out. Also, these mock test package, as I told you, so you can before the GATE exam, if you want to attempt some good quality mock test, then 15 mock test you can attempt. All the 15 mock test of Go Classes and GATEOverflow, all these 15 mock tests are available for you. You can subscribe for this mock test package. This package you can subscribe. If you already have complete test series, in the complete test series there are more than 100 tests, you can notice in the complete test series. So if you have complete test series, you already have access for mock test. Okay, so you don't have to purchase mock test. There is no need to purchase mock test if you already have complete test series. This complete test series, GATEOverflow plus Go Classes, this combined test series, this includes more than 100 quality tests. Okay, including 15 mock test. But if you only want to solve mock test, okay, before the GATE exam, if you only want to attempt mock test, then you can subscribe for our mock test package. The link is in the description, as I told you. Okay, so you can join. So thank you everyone, and so see you tomorrow. You can download our app also, Go Classes Android app. You can download from the Play Store. So search Go Classes on Play Store and you can download our app also. Okay, so thank you, and you can join our Telegram group also. So this is the username. The Telegram group link also you will find in the description. So actually, let me tell you, check out the description. This suggestion I will give to you, that just check out the description. Okay, check out description. In the description all the links are available. So check out the description. Okay, thank you everyone. So let me see if anyone has any doubt. So tomorrow in the first half in the morning from 10 a.m. you will have transport layer lecture. Sachin will take transport layer. We will complete the computer network marathon. Okay, so transport layer lecture is there from 10 a.m. and after that from 2 p.m. we have graph theory remaining part. Okay, from 2 p.m. we will continue our graph theory discussion. Anyone has any other doubt? Let me know. Okay, so operating system is already over. You can find on the Go Classes YouTube channel. That is already over. Or you can go to this course. Just go to this course. Okay, go to My Courses and go to this course, GATE PYQ video solution course. In this course you will find everything. In this course you will find OS also. In this course you will find DM, you will find CN, all these things you will find. Okay, thank you everyone. So like and comment on this session. Thank you and see you tomorrow. So tomorrow 2 p.m. we will continue our graph theory lecture. Okay, so thank you.